of required, ridiculousness that really doesn't have to do with stack misuse, okay? This is just too complicated a problem, or too complicated an approach. Okay, another thing that you can do very simply with recursion is to draw simple fractals. Now, these are kind of ugly. I'll show you a pretty one in a minute. But what you can do with this first one, for instance, is you can say, look, I'm going to draw a box, and then just to the right of it, I'm going to draw another box that's 80% of its size, or 90%, or whatever fraction you want to give it. And I'm going to keep doing that until I either get to so small a box that I can't draw it, or I exhaust what you would call a recursion depth, which says I want to go 10 deep and then stop, right? So that would be the super simplest example of a recursive, right, of a recursive thing. So here, for instance, I have a thing called draw box. I pass it the graphics reference so that I can draw where I want it to draw, X, Y, and its size. And I have a recursive depth counter as well. I'm starting here with the recursive depth of 20 that says I want to draw no more than 20 boxes. And notice that every time, here's my recursive case, if I either get to where I exhausted all of my depth that I was asked to do, or if the boxes are so small that I can't draw them, I don't need to draw anything. I don't need to do anything, in fact. So there's my base case, stop, right? Return. Otherwise, draw myself and then figure out where my child needs to go and tell my child to go draw itself. So I spin off another call to draw box. It's going to draw the child, but notice depth remaining goes down by 1. Right? So I always will eventually get to running out of the depth that I was asked to do, because this simplified the call. One more depth is taken in, and therefore we can do something like this. Okay, and so here is the output. It came up really quick on my other monitor, so I couldn't get it, to you in time. But there you go, right? That's not very pretty, but you get the idea. Draw a box, draw another box. It simplifies the problem as it goes until we get to 20 boxes or tiny boxes that we can't draw. And you can certainly do other things. This one is more like, I think of where I grew up and think of the Thunderbird pattern in some indigenous art. I think of that as a Thunderbird, but here's one that actually starts to seem like a real, right, like a real thing. And that is this fractal down here. So this fractal here is, this is how it's going to work. It's going to draw one box, and then it's going to spin off recursive calls to go above it, below it. I think it goes to the left next and to the right finally. So every one box is going to have 1, 2, 3, 4 boxes, alongside it that are smaller. Again, by whatever ratio here. So this is a 50% ratio of the smaller box to the original box. I also have this changing the color just a tiny bit so that every box is a slightly different color as we go. Right? But in this case, have each box has 4 children, so every recursive call calls 4 more. I also put a timer in here to where it will pause. So I have a pause, 5 milliseconds between every box. So now we can really see the nature of recursion here. Because watch what happens. I'll throw it quickly onto here, and you can see the thing actually being built. Grab it, hurry. Okay, so notice it went north first, and then it's sort of doing its recursive call, and then it will do south, all right? Then it will go to the left, yep. And then again, it pushes north and pushes north, right? And then eventually it will finish that thing, move to south, move to east, do to west, and then finally it moves to the right and does the box on the right. And now we would expect that when this is finished, the southern box is going to happen. There we go. The big box, then it pushes north again, right? Always this push north first, and it's going to continue to fill this out, changing the hues of the boxes ever so slightly until you get the whole fractal drawn, because it's fun to see it and sort of experience the, the way recursion's actually going about its work. Does that make sense? We'll probably get tired of that, so let's put the pause interval down to virtually nothing, maybe 1 millisecond or 0 milliseconds. And then let's just let it complete the whole thing. I probably can't even get it over to you in time to show it. Here we go. This is with a 1 millisecond delay, so this will draw itself pretty fast. And the recursion depth is like 5 or 6, right? So one big box, and then it'll branch out until it's at about 6 little mini boxes at the far ends. So this is more like what we would expect out of a real fractal, right? If you take out the pause, it'll draw virtually instantly, but I think it's fun to watch it a couple times to just see the nature of recursion in action here. There we go. Yay, done. Okay. Make sense? So that starts to feel like, a real recursive problem used in fractals. And I have, the recursion depth is 8 in this case, and then all the fun stuff that we just talked about with a little sleep in there to try to make sure we get a chance to see it a little better. Okay. All right. Any questions about how recursion is being used in those cases? Okay. So again, we're going to come to some other things that are fun. When we get to writing code for a binary search tree, we're going to look at recursion and think of it differently. In fact, we think we get recursion down until we have to go start writing stuff for like a binary search tree. And then all of a sudden our brain it kind of explodes a little bit. So, we will definitely have some fun writing those recursive methods for a binary search tree. But this at least gets you started, right? Gets your brain going in the right direction, thinking about the downsides, being careful with the stack, not being careless with it, and what some of the uses of recursion might be, right? So that's all I want to talk about regarding recursion. Again, we'll come back to it for 2 projects. Our binary search tree will definitely use